Okay, a rotor ride, or the gravitron. He's on here spinning around. We need this is Carlos, by the way, and we need a free body diagram on him. So obviously we will have some gravity acting down on him because he is here on Earth. This is a side view. We have a force up, but this time it is not the normal force. It says the floor is dropped out. He's stuck against the wall. So if he's not on the floor, what is pushing up on him? Not the normal, but is actually the wall scraping against him with friction that is preventing him from moving. So he is going in a circle. Here's the center of the circle. Something must be pushing him towards the center, and that is actually the normal force of the wall pushing against Carlos towards the center there. So that is part one. Then they have a simple little derive the expression for the normal force, and they only give you two little boxes. You might be like, what's going on here? Only two boxes? Well, I would start off with this. The sum of the forces must be a centripetal force because he's going in a circle. Well, the friction and the gravity are going to cancel each other out. Plus they're pointing perpendicular to the circle. The only one pointing towards the center is the normal force. So that's the centripetal force, and that's mv squared over r, and they write it as a capital R, so will I, and that is basically it right there. So then they say Carlos actually brings on a little sensor. Imagine he's puts a scale behind his back, and that's going to get the force of the wall right here, the normal force. And he gets a little accelerometer, let's say, and that gives him the speed of the ride. And we want to think of something that we're going to make a graph in order that we can get the right information of the radius off of here. So if we want the radius, and we're looking back to this equation here, let's sort of separate this out. This is a linearization question. So this side is already looking nice for a y, the normal force there. Let's take all our constants out. His mass is a constant, the radius of the ride is a constant. So I'm going to write it as the normal equals mass divided by radius times velocity squared. This makes it a bit clearer of how we're going to make our graph. This will be our y, this will be our x, because those are our variables, so v squared is our x, which means all of the constants will be our slope, and that will follow y equals mx with plus b, but no y-intercept in this case. So that is how we are going to set it up. So that means over here, what we are going to do is not use the speed, but use the speed squared in meters squared per second squared, or you could write the meters per second and square all of that. So 5 squared is 25, 8 squared is 64, 10 squared is 100, 12 squared is 144, and 15 squared is 225. We've already answered this question right here, what quantities should be graphed in order to get a straight line. We're going to do normal force on the y, and we're going to do speed squared on the x-axis there. Now, because it would take me a long time to write all of these out and make the video long to watch, I already wrote these out. So notice I have force, include your units, normal here, speed squared down here, with the meter squared, second squared units there. So I just tried to divide it out as much as possible. So going every 200 will get us up to 2,000 on the normal, just about the cap. And going every 25 will get us up to 250, just about the end there. And so I went ahead and plotted out all my points there. Some of them you have to do some estimation in order to get it. But now we need a line of best fit. So I'm going to line it up with the origin and try and get it as best I can right there. All right, so there is our line of best fit. Now remember, these points are not on the line of best fit, so I can't use them if they ask for the slope. This guy sort of and this guy sort of. What you want to sort of look for are nice intersection points there, because those are going to be easy to use. So I'm going to use that one right there, and I'm also going to use this one is about, in this case here, 200, that's about right in the middle there. So that would be a good point to use. Those are the two I'm going to use. And we want to use this to figure out what the radius is if his mass is 50 kilograms. Well, we talked about on the previous one that since normal is equal to mass over radius times v squared, this is our slope. So we got to find our slope and set that equal to mass over radius. So I'm going to do the change in the y over the change in the x. Our change in our y, we've got about, on this case, halfway up, so about 1,700. And down here, my y was 200. And then I'll do my change in my x over here. Here I have 200 for my speed squared, and I have 25 there. So when I subtract those out, I get a value of 1,500 in my numerator and 175 in my denominator, and that gives me a slope of 8.57. I've got to set that 8.57 equal to my mass over my radius, but my mass is 50 kilograms over r. So when we go to solve for r, we get 50 kilograms divided by 8.57, and that gives me about, in that case, 5.8 meters. You could obviously get some variation in there because your slope could vary by, your best fit line might have some variation in there because of how you scaled the graph.